I'm not trying to sell anyone a book today. I'm just trying to give you guys helpful advice to proceed forward from out of your PhD. So I mentioned this briefly. We're going to talk about what the things that I did as a PhD student to prepare myself for my current life as an engineer that I'm almost 4 years into doing. How the kind of things that I pursued as a student to prepare myself for that. And then we'll talk about a couple of other things such as networking. Really, this is helpful as they say this. How to learn the value of your time. How your ability to teach yourself things as a PhD student is really your superpower, and we'll do some thoughts before we get to the end and some question time. Okay, so how did I prepare to exit and go to industry as a graduate student? We're going to talk about what makes an engineer, the way an engineer thinks different from an academic thinks, and the ways that I applied that to graduate school specifically. So this is an important topic because generally speaking, more PhDs than ever before are headed straight to industry. You could find 100 statistics on this, how either the number of people who actually make it to a tenured professorship position, how narrow that percentage is, or just saying that across all disciplines, more PhDs are ending up in industry than at any other point in history. So thinking of the skill set that you need is pretty useful. So with this awareness from coming from my undergraduate program, I entered my PhD program with a plan for how I wanted to exit it. This was in part because I had done 2 internships in the aerospace industry already, one at Raytheon on the left and one at Lockheed Martin, actually up here in Washington over in Bothell. That was a pretty fun summer. Building lasers with Lockheed Martin. So from these internship experiences, I had an idea that at least the aerospace industry was a place I would enjoy going to after I graduated. And because of that, I gave myself kind of an internal thesis statement. Especially as someone who would have a PhD, I wanted to be in a position of engineering leadership, and I wanted to be able to sell that on my resume, not just say, oh, I want to do this in my personal statement. I wanted to have something I could actually point to that would be the proof that I had this particular skill set. So in the optics and photonics community, which is where I work and my expertise is in, about 2/3 of people consider themselves to be engineers. A good portion of them have degrees in engineering and work as engineers, but there's a reasonably large percentage of them that don't have a background in engineering and end up being an engineer. So with 2/3 of my industry identifying as engineers, I would have to be able to think and act like an engineer does. And there's a lot of kind of cliche things you could say about the difference between how a scientist thinks and how an engineer thinks. But a lot of what is important to an engineer is that as an engineer, especially at a big company, you're beholden to your customer at some point. Your customer sets requirements and expectations on you that you're designing to meet to and accomplish. As an academic, you may have your grant that you're having to report your results to up the food chain, but it's not usually as strict of a contractual environment with very strict boundaries on your performance. And as an engineer, you have to think and work in the requirement space. For example, in my work on the Roman Space Telescope, the Wide Field instrument, the primary science instrument, has over 650 specific requirements that govern different aspects of. Some of them are simple, the volume of the instrument. Some of them are very particular about the wavelength bands that things operate at, the thermal ranges that things can operate at. And we have to be able to think and work in this space. And requirements are a very unusual subset of language. They're all very strict, like the system shall, da, 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 and it's a very particular formalism that's used for this that is not necessarily natural. So I wanted to learn about how to think in this requirement space, because requirements aren't just useful as an engineer at a company. The point of the requirements is to really effectively define the project and the scope of it. It's helpful for you as the engineer as well, because once you have agreed to your set of requirements, it's harder for your customer to expect more from you that they haven't agreed to pay you to do. So it's a production for you as well to prevent that scope creep from happening. So generally, you want your requirements to only tell you the minimum of what it needs to be. They need to be very concise. You have to be able to achieve it. It needs to be a complete description of your project. You have to have each of them individually verifiable and unambiguous, so that way everyone knows what we're trying to accomplish with whatever project that you're making. Generally speaking, requirements follow a hierarchy of you've got a top line functional requirement that defines the overall goal of what your system is trying to accomplish. That usually doesn't have any numbers behind it. It just describes you, I want my thing to do this. And all of the stuff below that derives from that top level requirement that then starts to break into the number nitty gritty of whatever you're trying to do. Generally, most engineers don't actually deal with the top line stuff. Most of what we live is in the derived and allocated requirements. So allocated, the classic example would be like weight. For the wide field instrument, we're allocated so much weight of the observatory. We're allocated so much volume on the observatory. The derived requirements would be, if you have a functional requirement that I want to observe this binary star, then you do all of the derivations to decide what your angular resolution needs to be in order to actually resolve those two binary stars. So for example, I mentioned Roman already. These are some of the top line science objectives for the Roman program. You've got your high latitudes survey for spectroscopy and imaging to do all of this redshift and measurements. You've got a supernova survey that repeatedly is looking at these different supernova fields. These two drive a lot of the wide field instruments, spectral requirements, and the large field of view. The exoplanet microlensing survey drives some of the detector calibration requirements. Since we're doing gravitational microlensing, you have to have a really highly calibrated detector to separate those things. The chronograph derives the need for the chronograph instrument, so that way there's the separate instrument from us that JPL is making that's also flying on the observatory, and then all you guys can play with the remaining 20% of time on the observatory. So these are all the functional requirements. These don't tell us anything of those details that I mentioned. It doesn't tell you what wavelength region the observatory is looking at. It doesn't tell you how large it is, how much it weighs. All that stuff falls down from these top line requirements. And on top of that, if you have a requirement, you have to be able to test that you've met it. So it's important, especially when you're working a contract, to decide how much that contract costs, that you think about how you're going to verify all these requirements. So you do, at the beginning, you think about, okay, how are you going to test and you're going to meet your requirements. We're going to get to the optics in a second. We just got to get through all the engineering background before we get to the optics specifics here. So you do this process all throughout the design process of the mission or whatever project you're doing. You're making these requirements, you're doing your verification plans, you think about your equipment needs all throughout the lifetime of the mission. And typically you verify with 4 standard methods. Test, fairly straightforward. You determine the conditions you need to verify that you've met your requirements. Generally, the most rigorous form, it's what most people prefer to do, but it is very expensive. So sometimes the only way you can do it is by analysis, either because it's too expensive to do in reality, or because it's too small of a number to actually measure, or because you don't want to break your thing. And in order to do the strength to failure analysis, you just do it in finite element modeling instead of actually breaking your thing. Demonstration is not used as common, but it just shows that it works. There's not as much structure to the testing verification environment as in a test. And then inspection can be trivial or really time consuming. I had a senior design team that they had a requirement that the exterior of their thing be purple, because that was the branding of the company. It's like, okay, that's an easy verification. We don't need to use a spectrometer on that one. We can just all agree that it's purple on the outside. Code inspection can be exhausting because a code inspection requires you analytically prove that your code is going to do the operation that it says it's going to do. So if it's a long code base, it's a real hassle. Okay, so all of that engineering stuff is all the stuff that I realized that I could start working on those skill sets and teaching myself to think in that space as a graduate student. Obviously, if you've got something like James Webb that is partners with tons of other people and tons of organizations and billions of dollars, it's really important to have this formalism in place so everyone understands what their roles are and their contributions are to the total stack of information. But you can also use this for yourself, perhaps not with 650 requirements on whatever it is you're doing, but I decided for my final project in my PhD to think in this way and define my project in this way to help me finish up and to prepare for my time in industry. Another thing that I did is I used independent study credits to help teach an engineering capstone course all throughout my PhD. There wasn't a TA position for this. I approached the academics dean at my college and I was like, hey, can I get away with using independent study credits to help teach this class? And so I got to help bring over 30 projects from the beginning all the way to completion and building hardware, assembling and testing it. I learned an enormous, this is one of the smartest things I did in my PhD. All of the technicals, all of the papers that I wrote, this prepared me the most for my time in industry because I got to see so many projects where they tripped up and failed. And I got to see, I learned stuff about neural networks from the computer science kids that I had never experienced or learned about before. And I still get to help. These pictures are from, we sponsor projects now with my company through the same program. So I still get to help do a little bit of teaching, which is pretty fun. Since I wanted to be in an engineering leadership position, I also spent a lot of time in leadership positions in the student optics chapter. There was a dual SBIE OSA at the time, and now Optica student chapter that helped to broaden my leadership experience. Okay, so we'll get into the specifics of how I applied this in my research in a second. But I'll just give you a lightning fast multiphoton microscopy introduction since that is the area that I applied it in. So multiphoton microscope uses the physics of nonlinear optics, which I know some of you in the room speak. But generally, it lets you do some really neat stuff, in particular with biological tissue. So for example, if you, pancreatic cancer is an area that I did some work in. That's what this picture is from, pancreas. Pancreatic cancer, the way that you determine whether something is cancerous or not is usually during surgery. You take small slices from the cut region, you cut them into thin sections, and then you chemically stain it, and then you evaluate whether or not it's cancerous. It's a pretty time-consuming process, considering the patient is open on the operating table while you're doing that. So, but without the contrast and the thin slices, which with a normal light microscope, it's pretty difficult to see any actionable information. You have to be able to see the structure in the cells in order to determine whether or not it's cancerous. Now, what a multiphoton does with nonlinear optics, all of these 4 pictures are now prior to the stained image on the top left. We took pictures of the same location, and with these different nonlinear processes, which I won't go into, they give you information for free in a sense, because the physics of how the laser interacts with the sample gives you contrast. That allows us to remove one barricade of now we don't need to do the chemical staining process, and now we can assemble all that information into one pretty picture that has all that condensed. The other thing that nonlinear optics gives us for free is it gives us 3-dimensional information for free, because it depends non-linearly on the signal strength of the laser beam. You literally get exponentially higher signal at the focus of the microscope objective compared to anywhere else. So in this picture, this is a fluorescent dye. You have a higher energy beam being focused down at 488 nanometers, and that is energetic enough to excite the fluorescence transition anywhere in the cuvette where that photon is. But at the infrared wavelength, it's only doing 2-photon excited fluorescence right in your focus. So now you don't have to deal with all of that uncertainty and the depth. You've just got a nice little cone or nice little Z depth that you're getting this information. So these microscopes are pretty cool. I have a lot of fun. So one of the first projects that I worked on was this particular microscope that was a mirror-based microscope. Since you're dealing with ultra-fast fiber lasers, you have a broad laser spectrum. So having an all-mirror system is nice because you don't have to have any dispersion in your laser beam, and you keep that nice, beautiful pulse right to the finish line at the sample. The problem with this system is that with a 5 mirror system in the center, it was a real pain to align if it got misaligned. Because of how we had designed it, I had really no experience in thinking about aligning complex systems before. So this was mostly a adjust the knobs and pray situation. So really quite challenging if it got misaligned to get it into a diffraction limited performance. So this was a formative experience for me working with the system of getting great results with it, but weeping and gnashing of teeth every time you had to realign something. So what I wanted to do is I wanted to make a microscope. I wanted to make a microscope that was another all reflective system that would not be nearly as much of a hassle. In part for myself because I didn't want to have to do that alignment, and in part because I was planning on graduating and I didn't want to get emails all the time like, hey, sorry to bother you, how do I realign the microscope? So I wrote requirements for myself to structure the criteria for the microscope. So in this case, the customer is just me, but I wrote requirements off that. I told myself, okay, we have these existing microscopes. I want to use the same microscope objectives. I don't want to have to change them out. So this turned into a set of requirements. Okay, I want to use the full numerical aperture of the microscope objectives, so I get all of the performance out of them that they can give me. That turned into, okay, that means I need to have a beam expanding relay, which is what those 5 years were doing in order to accomplish this. And then specifically, the derived requirement is it has to expand incoming laser beam factor 4. Then I needed to be competitive with the previous system, but it needs to be a lot easier to use and design. So again, in requirement formalism, the microscope shall enable diffraction limiting imaging over its field of view. And the previous system could do up to a 10-degree field of view, so it had to be diffraction limited up to that field of view. And then on the easier to align, that is a separate requirement because a good requirement does not roll up multiple thoughts into it. They're separate, distinct statements. So in this case, the function requirement is that it's easy to align. And on the system level, I wanted to get rid of as many degrees of freedom as I could get away with. So that way you just bolt it down and it works. So these requirements and more were what I followed through the design process. I set up what my verifications methods were going to be. That's test, analysis, demonstrate, analysis on the right. And I had some stretch goals about the larger field of view. I think this is a useful experience for you as a student, especially if you have any thought of being an engineer. It's useful to give this a try and think about how you define your project this way. I found it to be very useful. So I found a new design that worked with off-the-shelf parts that met my requirements. This is a pair of off-axis parabolic mirrors from Thorlabs and some careful optomechanics. It could give me my near diffraction limited performance at 10-degree full field of view and still fairly good performance at 20-degree field of view, the full scan range mirrors I had. And then I did a detailed tolerance analysis to look at all of degrees of freedom that I had to see whether I could get away with getting rid of those and just bolting it directly to the table. So the 2 powered elements, the 2 OAPs, not surprisingly, had the most sensitivity in their position. But surprisingly, I was able to show that most of these could be degree or less angle misalignments or millimeter scale positionings, which is pretty doable. Especially since my professor has a CNC machine at his house and he could CNC machine the breadboard so we could put the posts at just the right spot. So this was the overall assembled system then. The 2 off-axis parabolic mirrors you can see pointed out in the diagrams have no degrees of freedom. They're on mounts that constrain their rotation, and the combination of optomechanics holds them strictly to the table so they can't rotate and move. And then there's the assembled system on the right, looking fairly similar to the simulated system on the left. Oops, backwards there. And I nearly met my goal of diffraction limited performance. We're fairly close to just like 20% larger than the diffraction limit in this particular system. So it worked pretty well, even without any adjustability. We met the large field of view requirement. There's a little bit of vignetting on the bottom of the graphs, but these are all just different samples. There's a mosquito leg on the right in 3D on the microscope, and then a couple of biological samples and a mineral sample on the bottom. So the system worked great. And we also were able to add a new capability to use stimulated Raman scattering in addition to the multi-photon processes that I mentioned in the lab. So for myself, writing the requirements helped me to prepare for my role in industry and helped me make an easier to use microscope. They helped me to make my own goals clear to myself. They helped me to set a standard for what was a successful exit to this project. They pointed out to me what the things I needed to design and analyze in order to meet those requirements. And they were helpful to communicate my objective to my professor, because he is also not an engineer, but this was a translation point between my thinking and his thinking that ended up working out really well for us. And I continue to use all of my skills on this now in the work that I do for the wide field instrument. We're in the requirement verification process now for the wide field instrument. It will ship to Goddard this summer for inclusion on the Space Telescope program. And all of this ability to think and talk requirements, I do this stuff all the time now. So what can you do now? That all of my presentation sections will have a little what can you do section as little takeaways from each section for you. So for yourself, think about now what your possible exit options are for your PhD. Whether it's going to industry or studying academia, just taking the time to write out what your possible exit options are will be very helpful as you think about. There's a lot of things you can do as a graduate student. That's the beauty of the experience, is that you can focus your time in so many different areas, but it's easy to just kind of do random things without realizing how you can choose to emphasize skill sets that are going to more directly point to your time in industry, or wherever you end up. I would look at careers of people on LinkedIn or connections you have through your department and find out what kind of skill sets those people use all the time that may not be skill sets that they, developed as a graduate student, but are things that you can start learning how to do now as a student instead of after you get your first job. And it's also helpful to go to career fairs and just talk to recruiters and look at job postings. What are the specific skill sets that people are looking for? Even if you're planning to graduate 5 years from now, you can look at that now and see how you can focus on that particular skill set on the specific work you're doing. Okay, so that's my specific experience, but we'll go into a couple of other areas of skill sets that are useful, like networking. It really is important as they say it is. So how did I end up here at Washington State, where prior to this fall, I knew nobody here at Washington State. Well, Devin reached out cold on LinkedIn to this guy, David Giltner, who has a whole business of helping people get PhDs out into industry, and told David he was looking for someone who had some industry background to do these talks. And David talked to my friend Matt Posner, who is also an ambassador with Optica the same year as me, and he said, oh, you need to talk to my friend Ben. So then I talked to David, and David made sure I wasn't a psychopath, and then he connected me to Devin, and here I am. Just the fact that I'm here is a real example of the power of networking. For getting my job at Ball, now BME Systems, getting this job was fairly easy because of the time I had spent getting to know the people who would come to career fairs. Laura Coyle, who's now my direct matrix manager, I talked to her in August of 2019 as I was planning on finishing at a conference in San Diego, and I got some pointers on her on the specifics of Ball's job search process. And Bob Brown, who came out to the University of Arizona pretty much every year, I had talked to him for years. He had seen my presentations. So when I told him, hey, I'm looking to graduate, it was that easy to get an interview set up and fly out and get to know people. And that was the same with a bunch of the other companies that I interviewed at in the year I was graduating, because I had spent the time building those relationships across my education. In optics and photonics, the third of the optics community reports getting their current job through networking. And that's just the direct portion that says networking. But if you consider some of these other sections, like I was recruited or I can contact the employer directly, which I would contend means you kind of have to know someone at that company in order to reach out to. This percentage can rise pretty high. So this is really a really critical skill to start developing and start building your network now before you're looking for your next position. And this whole survey isn't just of industry positions, this is all positions. So as a student, you have a lot of really unique opportunities that give you chances to network. Colloquium events like this, any other talks that happen on your campus. A lot of the professional societies have special travel grants just for students to get you to go out to conferences and school events. The Optica Foundation has a large number of school programs like the Siegmund School, that's a week-long program on lasers that they massively subsidize, so that way students can go out and learn from world-renowned experts and with a bunch of their peers. That is just for current students. So these are unique opportunities not to miss out. Of course, there's the career fairs that I mentioned already previously. And there's a lot of information on LinkedIn as well. A lot of companies will post the same job postings on LinkedIn compared as on their website. And it's a good place to keep your feelers out to what's happening in your industry and your community, especially once you connect with a few or start following a few people that are talk a lot about the state of the industry. You can hear a lot very quickly on LinkedIn with that set of information. Okay, so again, what can you do now as a student? Well, I found a tremendous amount of benefit from being involved in professional society chapters, in part because that's how I learned about all of those schools and travel grants that I mentioned. So whether it is with APS, the AES or IEEE or whatever it is, there's lots of opportunities for you to have your own student chapter and get travel grants and traveling lecturer grants to come bring people out to talk to you. Make sure you take advantage of those opportunities while you're a student and while membership is very, very cheap compared to professional membership. I would ask anyone who has money to send you to a conference. This is still true for me as a professional. People at my work have frequently asked me, like, how do you get to go to so many conferences? It's like, I'm just obnoxious enough to ask people who have money, like, hey, can you send me to a conference? They might say no, but I don't really lose anything in the process by asking for money to go to an event. So whether it's talking to the department chair for money or your PI or whatever, maybe your graduate student association has travel grants for students, I don't know, but look for ways to send yourself to a conference. And getting involved in LinkedIn, as I mentioned, is a good way to have those easy connections and find people that can help you out in the future. I'm gonna do it on time. Okay. Speaking of time, this is the area that I failed at as a graduate student. I did not appreciate the value of my time until I finished and got out into industry. So as you might expect, the value of your time in a graduate student is a good bit less than the value of your time when you're out in industry. None of us became wealthy as graduate students, unless you invented something and started a company off of it. These are stats off of the Bureau of Labor Statistics comparing general teaching assistants and folks out in the aerospace industry. And if you compare those numbers to the SBIE salary survey, which is a great source of information, by the way, I pulled a couple of graphics from the SBIE salary survey. It's a pretty similar story. The survey contains global results, but generally it's a significant contrast in the value of your time. So as a student, I never bothered how to learn analysis tool APIs. If I was going to design an optical system, I would just go into the GUI and spend a bunch of time clicking and getting analysis results because I just I wasn't making new designs or analyzing large amounts of data. I didn't have a reason in my mind to teach myself how to learn the APIs. It all seemed like more of a hassle than just pulling down the graphics quickly for myself. But I realized very quickly when I got to my company that More experienced people get more done, not just because of their additional experience, but because they know how to do it much more efficiently than I did. And some of it is that these people have huge folders worth of MATLAB scripts that can do all of these large analyses automatically. They've either, when I started, I got 3 huge folders from different people of all of these programs. Man, this could have saved so much pain and time if I'd known how to do this already. And there's a lot of tools that have this built in. Whether you're a Python person or a MATLAB person or whatever your flavor of coding is, there's a lot of ways you can learn how to do this. I know you astronomy folks deal with a lot more big data, so maybe this part's obvious to you guys, but to me, this was a big shock. And in my job, I had to learn how to do this quickly because for predicting flight performance for the wide field instrument, I would frequently have hundreds of interferograms of measured optical data that I would have to simulate how that would impact on the observatory. And obviously I cannot like go into code 5, apply this to the surface, run the simulation, come back, go change it and do that. I can't do that by hand. It'd be an enormous amount of time. So I had to learn how to ingest data and apply it and simulate it automatically, or I just would have drowned in the tasks that I had to do. And we're kind of in a strange new world of task automation right now. There's so many new AI tools. It seems like you could read an article every week about, oh, they're making video now automatically. Oh, and they're doing all this automatically. There's so many different ways that you can start to do some of your paper research automatically or reference finding automatically. I mean, some of that existed, but there's a lot of the space that is, I have no idea how this is going to impact the way that we approach getting computer tasks done. So what can you do now? You can start to work to build an awareness of the value of your time, whether that's through thinking like, okay, my hourly rate is like $20 an hour, say, and this part costs like $2,000. How much of my time is it worth agonizing over this $2,000 purchase versus just buying it? You can learn how to use some APIs to talk to the key software tools that you use. And if you have to do a particular analysis task more than twice, that's usually the breaking point where it's faster just to code it. Try scripting it instead, especially if you don't have any prior scripting experience. Okay, so on one of my last points here, you're on ending on a high note here. As a graduate student, your learning ability is your real strength. You guys have taught yourself how to teach yourself, and that will carry you through any position that you might end up in. Especially in industry, very few PhDs do exactly the same thing they do in grad school in industry. Part of that is just that you get so specialized towards the end that there's maybe like 5 places you could do that very specific thing. But part of it is just that you have, your skill set is so needed that it's easy to go anywhere other than specific sectors. So for example, when I entered my PhD, I knew nothing about pancreatic cancer other than that it was bad. So, but through working with a medical doctor on campus, I got to write several papers about pancreatic cancer from the work that we did, which meant that I had to spend time in medical journals learning their terminology to write the introduction for the paper and see what was important. When I entered my PhD, I knew nothing about gems and minerals, but we did some cool projects using the multiphoton microscope, looking at gems and minerals and taking really pretty pictures, where again, I had to spend time in the geology, geoscience journals to look at these pictures and be like, I have no idea what I'm seeing. Maybe this is flow banding and obsidian that we're seeing in second harmonic generation. And now at Ball, I knew nothing about astrophysics, but I now have had the chance to learn stuff about astrophysics. I know a lot more thanks to Guy and dinner last night. But I've had to learn how to see what is important to the scientists for the missions that we're trying to accomplish. And in my case, from a technical perspective, there were some overlaps because I was designing off-axis mirror-based microscopes. Off-axis mirror-based telescopes is pretty similar from an optics standpoint, but all of the science applications just totally different. So the thing to take away for this last section is that your skills and your experience are much more transferable than you think. because your inherent learning capability, your inherent drive as a PhD student, it really doesn't take necessarily a brilliant person to do a PhD. It takes a person with enough drive to power through the experience of, well, I don't know how to do this, but I looked online and turns out nobody knows how to do this, so I guess I have to figure it out. And you have that experience enough time that builds that mental resiliency in you, and that is really, really useful and transferable. So what you need to do, especially if you're applying to a job that's outside of your specific degree, you have to describe yourself this way on your resume. Leverage your learning capabilities in your resume and the description of yourself, so that way people know that this is one of your superpowers as someone with a PhD. Okay, so I have a couple of concluding thoughts, and then we can take some questions here. We should have some good time for that. Okay, so just capping up my main point here, beginning your PhD with the end in mind. Whether you're at the start of your PhD or you're about to finish, you can start thinking about your next step now. Think about how you're going to describe yourself. Think about the skills that you can hone as a graduate student and the incredible flexibility that you have as a graduate student. Learn about the industries that people at your university have already gone to in the past. Think about how maybe you can think about like how a data scientist thinks, because that's an area that all of your data handling experience is really useful. A lot of this does require networking and time out in the community. I had seen that David Giltner is going to be here in April, and he's going to talk all about networking, so you can get a much longer period of time learning about networking from him. But really helps to have a network. Look at job postings online and see the skill sets that are out there and how you can focus on those skill sets, and start thinking about value of your time and how you can start learning to automate tasks to make yourself be more efficient, which will help you now in the work that you're doing, even if it will also help you in others. So there's a lot of resources out there to help you keep learning. The Optica ambassadors, there's about 80 of us now that are all early career professionals that we all do various workshops and webinars that you can find us on Optica's homepage to connect with. There's people in just about every discipline and all over academia, all around the world. So there's my friend Truly wrote a great article that has a bunch of these pieces of advice on optic and photonics news, all detailed out. Similar points to some of the ones that I made, but it's a really nice, well-written article. And in addition to the 7 Habits of Highly Effective People books that I mentioned, these are 4 books in particular that were really useful to me. The 2 books on the left are all about how habits are really useful and how companies build habits or companies build productivity into their methods. Really helpful mindsets towards the end of my PhD that I was able to get from these. And the 2 books on the left or the right are more pure businessy books that just talking about what makes a business great and what makes another business really mediocre. So again, just kind of thinking mindset kind of things that I thought were really, really useful. And these books have all been out for a while, so you can usually find them for like $5 at used bookstores. They're good reads. Okay, so thank you so much for having me once again. Thank you all so much for listening to what I had to say. I hope my story and my examples have been inspirational or encouraging to you that going out into industry is something that you can definitely do and be successful at as someone with a PhD. So thank you.
So what were some of the most worthwhile things you did through SCIE and Optica as a chapter?
So there's probably the two most beneficial things that I did is I organized and what's called an IONS conference, International Optics Network of Students conference at my university. And it's the most complicated project that I ever tried to take on because we were bringing people from 8 different countries and all around the US to come to this conference. I learned a lot about project management. I made a lot of mistakes in how I allocated work to some people. I burned out some people and other people didn't have enough to do. So that was a really useful leadership experience for me. The other thing that was really impactful was attending the Siegman School that I went to that was in Denmark in 2018. Just meeting people from all around the world, many of whom I still stay connected with on LinkedIn and have seen in person. It just really opened my eyes to the international nature of science and yeah, it's a really amazing learning experience for me.
You mentioned you did a couple internships. Were those as undergrads or grad student?
I did the first two were as undergraduates. I did the Raytheon and Lockheed ones that I showed the pictures of were both as an undergraduate, but I did do one internship as a graduate student. My family's in Tucson where I did my PhD, so my wife and I were trying to decide if we wanted to stay in Tucson and just didn't have a great experience, so we ditched.
So to follow up with that, how did you find your internships? Through networking, or were there other sources in which you used to look for either like internships or fellowships or things like that to broaden your experience base or after your PhD?
So that internship, because I had worked at Raytheon once before, was pretty easy to get because I knew a bunch of people then, and I told them that I wanted to come back and try it as a graduate student. But yeah, all of my, with the exception of the Lockheed Martin internship that I applied to a bit more cold, pretty much all of my positions have been through known people. Other questions? Yeah.
When it comes to networking and approaching, do you find that it's like better to try and be friendly with them or like try to impress them?
I mean, I guess to some degree it depends on the environment. Usually at conferences, there's a lot of really informal ways to meet people and get to know them that doesn't necessarily involve impressing them. But I did at the career fair at my university, there was an option to give presentations on your work. And in that case, I was trying to impress all the potential recruiters by showing off the work that I did. So yeah, it can be a tricky balance. You definitely don't want to walk up to someone at a conference and be like, "Hi, I have 7 first author publications." They'll be like, "Hi." Yeah, depending on the circumstance, you're trying to walk that one. Yeah.
So I'm just curious, so you got through with the 2 internships as an undergraduate, and being ready to go to graduate school. What made you choose physics or physics related as opposed to an engineering graduate school? It sounded like you had this plan all along to be an engineer, and so what was the thinking?
Well, so the University of Arizona is a fairly engineering heavy optical sciences program. There's 4 main subdisciplines within the department. It's a very big optics program if you haven't heard of it. And engineering is the largest subdiscipline of that. So yeah, my PhD isn't in engineering per se, but it is a very engineering, there's a lot of courses in engineering that I got to take as part of the program. Did I miss any questions online? No, it doesn't look like it.
Any other questions? If not, let's thank Dr. Cromey again.